At 4:37 a.m., about 40 kilometers south of Sri Lanka, a Los Angeles-class attack submarine was carrying out one of the most classic missions of submarine warfare, tracking an enemy ship. Approximately 13 kilometers ahead sailed the Iris Dina, one of the few remaining operational surface combat ships of Iran. The ship zigzagged at about 28 kilometers per hour, emitting pulses of active sonar as it tried to pinpoint exactly what was following it. Soon, CENTCOM would send the submarine's commander an order that virtually no American captain had received since World War II. But before we begin, don't forget to like and subscribe to our channel. Before that, however, the submarine needed to solve a fundamental problem, finding a firing solution. The Dina scanned the ocean with active sonar, while its ASR 3D radar monitored the entire horizon. To complicate matters further, every 3 to 5 minutes the Iranian captain unpredictably altered course, continually resetting the American crew's calculations. Submarines that hunt using passive sonar typically detect only the target's direction, not its distance. It's like having only a compass. You know where to go, but you don't know if the destination is a few kilometers away or much further. In the fire control center, operators watched the Dina's heading line slowly advancing on the monitor. By measuring how this direction changed over time and applying target motion analysis, TMA calculations, they were able to estimate the ship's distance, speed, and heading. Gradually, the firing solution began to appear on the screen. But every time the data started to fit together, the Iranian captain changed the ship's course again. The calculation line would become scattered, half the work would be lost, and the process would have to start over. It was like trying to calculate the distance of a car just by the sound of the engine while the driver constantly changes lanes. That was the silent battle the fire control team was facing that morning. The Iranian captain had spent 2 weeks on the multinational naval exercise Milan 2026 with the Indian Navy, training precisely in these anti-submarine warfare procedures. The Americans had been watching. Now one of those submarines was following the Dina like a patient ghost, and the Milan training was the only card he still had to play. But that wasn't what worried the crew most. What truly concerned them was sitting in the flight deck aft of the Dina. The SH-3 Sea King anti-submarine warfare helicopter carried a low-frequency dipping sonar designed to do one thing: find submarines where hull sonar can't reach. Think of it this way: Dina's hull sonar screamed into the ocean from the surface, hoping to hear an echo. The submersible sonar descends directly into the submarine's living room. Sea King helicopter could launch a sonar sensor through the thermocline, bypassing the acoustic shielding that concealed the submarine. Below this layer, the microphone would operate in the same sound environment as the submarine, making it possible to detect it quickly. Dina's helicopter crew could move across the ocean in leaps, scanning the area much faster than any surface vessel. At 120 meters deep, the submarine couldn't see the surface, only hear, and any sound of the helicopter taking off would be a sign of danger. If the helicopter took off, the Americans would have only 2 options: fire immediately or dive deeper and lose the opportunity to attack. Although the thermocline was deflecting the sonar pulses and making the submarine appear invisible, it was not a perfect barrier. Sound in deep water could bend and return to the surface in convergence zones about 55 kilometers away. If a sonar pulse from Dina hit the correct angle, it could unexpectedly reveal the submarine's position. To make matters worse, the thermal layer was thinning. Technicians had been launching disposable bathythermographs to measure the surrounding water. 3 clocks were now ticking against them. The thermal layer was weakening by the hour. Each new reading came back warmer than the last, and the sonar chief estimated between 6 and 8 hours before the layer would degrade beyond the point of reliable occultation. The Dina was sailing practically parallel to the coast of Sri Lanka at about 28 kilometers per hour. Maintaining that course and speed, it would cross the 22-kilometer territorial boundary in approximately 40 minutes. Once that happened, any attack would become impossible under international law. And on the aft flight deck, the Sea King remained provisioned, armed, and a single order from the captain to transform the submarine's hiding place into an open-air auditorium. Any one of those clocks reaching zero would end the mission, and all three were running simultaneously. At 4:41 a.m., with the thermal layer weakening, the helicopter one launch away, and the fire control team struggling to calculate a zigzagging target in the middle of a noisy ocean, the submarine needed something it couldn't receive at that depth. The authorization to operate CENTCOM did not reach operational depth. The ELF radio, an extremely low frequency, the only signal that can penetrate deep water, has virtually no data transmission capability. Think of it as the most expensive text message in the world, and all it can say is, "Call me." That was enough to order the submarine to rise to shallower waters, but not enough to transmit the attack authorization for what would come next. To receive the full order, they would need to rise to periscope depth. This meant leaving the thermocline that kept them hidden, entering the water column where Dina's hull-mounted sonar worked best, raising a communications mast above the surface, and entering the detection envelope of the ASR 3D radar that was scanning the sea for exactly the kind of tiny contact a periscope creates. To communicate undetected, the submarine needed to raise a mast above the surface, something extremely risky, as it could appear on Iranian radar. The solution was to use a South Korean LNG tanker, which produced a huge radar echo. The submarine waited until it was aligned precisely between the oil tanker and the Iranian ship Dina, remaining hidden in the cargo ship's radar shadow. This way, any return on the radar would appear as mere interference caused by the large ship, not a submarine. At 4:48 a.m., the submarine ascended to periscope depth, crossed the thermocline, and rapidly raised its communications mast. Satellite contact was established. Attack authorization was confirmed, and the submarine dove again below the thermal layer, regaining its invisibility. Meanwhile, the Dina continued advancing eastward in a zigzag pattern, emitting sonar. But the tactical situation was becoming increasingly tight for both sides. At 4:51 a.m., and the Dina's course ran parallel to the coast of Sri Lanka, about 37 kilometers offshore, while the 22-kilometer territorial limit was approximately 15 kilometers to the north. International law made those waters inviolable. If the Iranian captain became alarmed and turned toward the coast, the opportunity for attack would simply vanish, and a captain who had seen his navy so badly damaged had every reason to stay close to the coast. His crew would rather be interned by Columbus than torpedoed by something they couldn't see. With each passing minute the submarine waited, the Dina moved closer to the line, where a single change of course would take it into the protected zone. Another limitation still loomed from behind. The submarine was still dragging its towed sonar, hundreds of meters of sensor cable stretched behind the vessel, its most sensitive ear. But the moment the torpedo was launched, if the submarine needed to maneuver sharply, that cable would become a leash. It couldn't be retrieved quickly. Aggressive maneuvers could tangle the cable or simply break it. The submarine's best sensor was about to become its biggest problem at the worst possible moment. At 4:53 a.m., the fire control team locked in the solution. The weapons officer programmed the Mark 48 AD cap torpedo into Tube 1. The captain gave the order. And what happened next was the loudest sound the submarine would make that day, in an ocean where Dina was listening precisely for that type of noise. The submarine flooded the torpedo tube and launched a Mark 48 torpedo, a critical moment that could have been detected by the sonar of the Iranian ship Dina. The crew relied on the thermocline, the intense maritime traffic, and the natural noise of the ocean to mask the sound of the launch. The torpedo, weighing approximately 2,600 kilos, used a monopropellant engine and a pump jet propulsion system, which prevented cavitation and left no trail on the surface, unlike older torpedoes. Its only signature was a faint acoustic noise, almost imperceptible in a busy shipping lane. During the initial run, the torpedo was guided by a wire connected to the submarine, allowing the operator to correct the trajectory, avoid obstacles, and react to the target's maneuvers. However, this forced the submarine to remain practically motionless, as any maneuver could break the wire. While the torpedo was traveling at over 100 km/h, the operator guided it blindly for about 13 kilometers to the Dina. If the ship changed course unexpectedly, especially towards Sri Lankan territorial waters, the technician would have only seconds to adjust the course using that extremely thin wire before the torpedo could acquire the target on its own. 8 kilometers away, Dina changed course again. The direction changed on the fire control monitor. The technician adjusted the torpedo's gyroscope via the wire, bending the interception geometry to follow the new course. Each correction consumed more wire. Each degree of curve decreased the margin between a guided weapon and an expensive noise generator. 6 kilometers. The continental shelf off Galle, Sri Lanka, plunges abruptly into the deep waters of the Indian Ocean. The depth gradient compressed the torpedo's performance envelope from all sides. Too shallow, and the weapon could surface. Too deep, and the run time would increase, giving the Dina extra seconds to turn or escape. The three-dimensional maneuvering box that the navigator had been controlling shrank with each kilometer. 5 kilometers. The Dina emitted another sonar pulse. The acoustic wave spread through the water, passing over the torpedo like a spotlight sweeping away a thief in the dark. The Mark 48 was small and fast enough that the echo, if it appeared, would probably have seemed like mere biological noise on the Iranian sonar screen. Probably. The word submarine crews learned to live with. 3 kilometers. The Mark 48 slowed down. The flow noise dropped, and the torpedo woke up. The internal sonar, a two-dimensional electronically guided phased array seeker, began scanning the water ahead. Active pulses. High frequency. A 1,500-ton frigate sailing at 28 kilometers per hour, displacing water in the Indian Ocean, is no subtle target. The sensor locked onto Dina almost instantly. Terminal acquisition. As the torpedo entered its final attack phase, the Iranian ship Dina finally detected the danger. A sonar operator heard the torpedo's active pulses, a sound indicating a weapon rapidly approaching in a steady direction, i.e., on a direct collision course. The alarm was triggered and the captain was alerted, but only 15 seconds remained until impact. Although the ship possessed acoustic decoys to deflect the torpedo, the process of recognizing the threat, authorizing the response, and launching countermeasures would take more time than was available. Maneuvering was also not feasible. A 1,500-ton frigate traveling at 28 km/h needs hundreds of meters to complete a turn. Dina's torpedo launchers could hit distant targets, but this required precise positioning of the submarine, which remained hidden 120 meters below the thermocline, invisible to sonar. Even if the decoys were launched in time, the torpedo could still be manually guided by the submarine via a wire, allowing the operator to bypass countermeasures and direct the weapon straight at the actual target. Therefore, the submarine remained completely still throughout the attack, preserving the wire that maintained control of the weapon until the very end. The Mark 48 did not directly hit the hull. It passed under the keel and detonated at the ship's most vulnerable point. The magnetic fuse detected the large mass of steel above and triggered the explosion directly beneath the main structure. The detonation created a huge gas bubble that violently expanded upwards, lifting the ship's stern out of the water. It's like bending a metal ruler until it breaks, except that this ruler weighs 1,500 tons, and the force bending it is a column of superheated gas exploding beneath the hull. For a brief moment, the frigate hung suspended in the air without support from its keel. The ship's structure was forced beyond any designed limit. When the bubble collapsed, the stern fell back into the sea and the keel broke. Periscope images released by the Pentagon hours later showed the bow rising against the sky before dawn, while the stern dragged the rest of the vessel to the bottom. In a few seconds, the 94-meter Iranian ship folded in half and disappeared beneath the Indian Ocean. At 5:08 a.m., the distress call was transmitted. When Sri Lankan rescue vessels arrived at the scene, they found only oil slicks, wreckage, and a few lifeboats scattered in the early morning current. Meanwhile, the submarine had already returned silently below the thermocline. No periscope, no transmissions, and no trace left behind. The towed sonar continued to be dragged behind the vessel, as if it had all been just another exercise. The nuclear reactor hummed softly. The ocean closed over the spot where the ship had been moments before, as if it had never existed. If you enjoyed this content, also check out our video about the first day of Operation Epic Fury. Until next time.